Hi, today we're going to talk about inverse functions, and we're going to talk about the link between the inverse functions that you studied in pre-calculus class and inverse functions in trigonometry. First of all, let's do a quick review of inverse functions from pre-calculus. In pre-calculus class, I learned that if I take an equation y equals 2x plus 3, I can get the inverse of this particular equation by following a certain procedure. And that procedure is to replace my y's with x's and to replace my x's with y's. If I do that in this particular equation, I get x is equal to 2y plus 3. The second thing I'm going to do in this particular equation is solve the equation for y, which is mathematical code for get the y alone on one side of the equation. To do that, as I look at this equation, I am going to subtract 3 from both sides of the equation. Now my equation looks like this. Next, to get y alone, I'm going to replace or divide both sides of my equation by 2. If I divide both sides of my equation by 2, I find that y is equal to x minus 3 divided by 2. Now, I want to show people that there's a relationship between my original equation and this new equation. This is my original, and this is my inverse equation. To show that there's a relationship between these two equations, I'm going to use a different kind of mathematical notation. And that notation is going to be this. Instead of saying y equals 2x plus 3, I'm going to say f of x is equal to 2x plus 3. And instead of saying y is equal to x minus 3 divided by 2, I'm going to write something that looks like this. If you remember from pre-calculus class, f inverse of x is equal to x minus 3 divided by 2. This notation does not indicate an exponent. This notation of the -1 indicates an inverse, and in particular, f inverse here is the inverse of my original f function. Now, if I can do this in pre-calculus class, I can certainly do it in trigonometry as well. And so if we move on to trigonometry, and I look at the function f of x is equal to the sine of x, I say, well, there must be an inverse for this function too. I'm going to replace f of x with y. And now I'm going to follow the procedure that I did above. I'm going to replace my y's with x's and my x's with y's. The only difference is, now to follow the second part of this procedure, I need to get y alone on one side. And I'm certainly not going to do that by dividing both sides of this equation by sine. That's not particularly legal. So what we do in trigonometry is this. We say that y is equal to the inverse sine of x, and you can see that's my inverse notation, that -1. Or in trigonometry class, we can also say y is equal to the arc sine of x, and these are two different ways of saying the same thing. Some books like to use the inverse notation, and some books like to use the arc notation, but they both mean the same thing. Now, originally, when I had y is equal to the sine of x, I know that this was an angle. For example, the sine of 30 degrees, and that the sine of 30 degrees produced, for example, a ratio. So this y over here stands for that ratio. But now that we've swapped our x's for y's and our y's for x's, when I write y equals the inverse sine of x, this x is not going to be an angle anymore. It's going to be a ratio. And over here, what I'm going to be looking for when I see this kind of notation is the angle that produced that ratio. And in particular, I want that angle to be in radian measure. Okay, so for example, if I were to give you y is equal to the inverse sine of the ratio 1/2, you would tell me that y is equal to the angle that produces this positive ratio for sine. Let's think about what angle that would be. What angle is it that produces the positive ratio 1/2 for sine? It's a 30-degree angle. Oh, but right, I need to report that in radian measure. So instead of saying 30 degrees, I'm going to report my answer is pi over 6. That's one part of our review concerning these angles. A second part of our review concerning these angles is going to be about the graphs of functions and their inverse. If I were to say y is equal to x cubed, I know what the graph of y equals x cubed looks like. I can sketch it from my pre-calculus knowledge. It looks something like this. And now when I look at this graph, I can tell that this is the graph of a function because if I hold my ruler vertically at any location on the graph, it passes the vertical line test. That's a test to see if this is a function. So the vertical line test is testing to see if I have a function. We also learned in pre-calculus class that to see if a function had an inverse, we held our ruler horizontally. And when we hold our ruler horizontally, if it only hits one particular part of the graph at a time, that is the test to see if that function has an inverse. So the horizontal line test is a test to see if I have an inverse function. Do all functions have inverses? And the answer to that question is no, they don't. For example, if I were to look at the equation y equals x squared, I know what that looks like again from my pre-calculus class. That is the function, a parabola, a very simple parabola whose lowest point is here at the origin. I can see that y equals x squared is a function because it passes my vertical line test. However, it does not pass the horizontal line test, so it's not going to have an inverse function. However, if I wanted to, I could force this to have an inverse function. How could I do that? I could limit the domain of y equals x squared. For example, I could say y equals x squared where x is greater than or equal to 0. Let's see what happens to my function if I were to limit its domain. Now my function looks like this. It only exists where x is either equal to or greater than 0. And now my function is still a function, but look, it will have an inverse. And we get an inverse function by limiting the domain of my original function. And we're going to see that in our next video that works out pretty well in our trigonometry class. If we look at some of the videos or we look at some of the functions, sine, cosine, and tangent, and we limit their domains, we're also going to be able to have inverse functions in trigonometry.